Section 4.8 now, and we're going to look pretty closely at acid and base reactions. So we are going to use the Bronsted-Lowry definition for acids and bases. Okay, so there's going to be a transfer of one or more protons between an acid and a base in one of these reactions. So the acid is going to be what donates the proton. It will give off the H plus in solution, and the base is going to be the proton acceptor and what would take the H plus ion out of the solution. Okay, so essentially what we're having here is the acid is donating the proton and giving it to the base. So we've already looked at Arrhenius and Bronsted-Lowry's definitions of acids and bases. And there's another definition known as the Lewis acid and base, but we are not going to worry about those or that definition in this course. Okay, that is something that you will see a little bit more commonly in an organic chemistry class. So we're going to look a little bit at water. So I want you to kind of think about right now, how can you describe a water molecule on the basis of the molecular structure, the intermolecular forces that a water molecule might cause, okay, how it might interact with other molecules, or in this case, ions, okay? And how do water molecules contribute to the dissolution of salts, as we talked about before in that whole process. All right, so the structure of a water molecule, we got the oxygen in the middle with covalent bonds to two different hydrogens. There is a bond angle. Remember that this is a bent structure because there are two bonds and then two lone pairs. So for that type of shape, the angle would be about 109.5, but because there are several lone pairs here, that's going to compress our angle to less than 109.5, so about 105 degrees. Because of the difference between the electronegativity of our atoms in these bonds, that means that the oxygen, which is more electronegative, is going to hold the electrons closer to it, making it partially negative and making the hydrogens partially positive. So when a salt is put into water solvents, what will happen is the water molecules are going to come along and they're actually going to break apart the ionic lattice because of the fact that the partially negative and the partially positive ends of the water molecules will attract the positive and negative ions that make up the lattice here. Okay, so you can think of like sodium chloride. The negative ends of the oxygen will be attracted to the sodium, which is positively charged, and then the positive charges of the hydrogen atoms will be attracted to the negatively charged chloride ions. Okay, so if something is conductive, then that means that it is able to carry an electrical current. Pure water, which would have no ions, or we could call it deionized water, will not conduct electricity. So there has to be electrolytes present in an aqueous solution for it to be able to conduct electricity, because then those charged particles would move within the solution in conducting the electricity. So something that would be considered a strong electrolyte, something that we would put into water which would not normally conduct electricity, would then, in being added to the water, conduct electricity very efficiently. So that would, like, if you think about the experiment that we did, when you put that our little light bulb into the solution, it would make the light bulb turn on very bright. Or if it is more of a weak electrolyte, the light bulb would not get quite so bright. And if it is not an electrolyte at all, then it would not make that light bulb turn on at all. So Arrhenius was really the first person to come up with this idea of electrolytes in studying acids and bases. And he said that his postulate here for conductivity says that the extent to which a solution can conduct an electric current directly depends on the number of ions present. So the more ions, the better it will conduct the electrical current, the more current it would be able to conduct. So, you know, he did this before the atomic model even came out. And once atoms were found to contain charged particles, so the positive and the negative protons and electrons, this postulate was accepted. And strong electrolytes are going to be ones that completely ionize in water. So that can include the salts that we've been talking about, but that also includes acids and bases. Because remember, acids are going to release positive H plus ions, and bases will, in most cases, release OH minus or hydroxide ions. Okay, so a strong acid will behave as a strong electrolyte because it will completely dissociate, meaning that it will release all of its hydrogen ions in solution. But not only that, so in this example, it's all the hydrogen and all of the chloride ions will dissociate in the water. So all of these molecules would dissociate when dissolved in water. Same thing with nitric acid, same thing with sulfuric acid. All three of these are strong acids and they will completely dissociate and form the H plus ions plus whatever the ion would be that is also contained there. Okay, so this is the basic equation here. This is something that we will look at much more deeply moving forward. But HA, so the acid, which is represented by A, has at least one hydrogen ion, plus water will yield the hydronium ion, which is H3O plus, and then the A minus. Okay, we could also write this as just H plus. Okay, if we just eliminate the water, we could just write it as HA aqueous yields H plus A minus. Okay, so there are 7 strong acids, and these will be ones that you should definitely know. But they are hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, chorus acid, and then chloric acid. Okay, so those are our 7 strong acids. Bases can also be strong, basically meaning that they will completely dissociate into whatever the cation is plus hydroxide ions. There are 8 strong bases, and as you can see here, they are all hydroxide salts, and they are either the alkali or the alkaline earth metals. So we have lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium hydroxides. All of these are considered to be strong bases, meaning that when they're put into water, all of the hydroxide and whatever the cations would be are released. Okay, they dissociate completely. There are also what would be called weak electrolytes, and there are weak acids and bases. So they will only partially dissociate or ionize in water. So we could have, so like in this case, these are, acetic acid. And like in this example, there are 5 acetic acid molecules and only one of them dissociates and releases a hydrogen. Okay. So basically what all that a weak electrolyte means is that not all of the molecules that are put into solution would dissociate. Okay, so in this case, only 1 out of the 5 does. So we would represent the reactions, okay, if we're writing out the equation with a double arrow, meaning that, okay, well, it will proceed this way, but there's also the possibility of it actually proceeding in the opposite direction too. Okay, so we have our weak acid here with acetic acid, and we also have our weak base, which in this case is ammonia. A conjugate base, excuse me, sorry, oops, went too far. So there are things called conjugate bases and conjugate acids. A conjugate base is going to be whatever the weak acid was after it loses its proton, okay? And at that point, it will then be able to accept the proton. So in this case, we have acetic acid, and after it loses the hydrogen ion, it becomes acetate, okay? So this would be our conjugate base, okay? So whatever the conjugate base is, that is the conjugate acid minus its proton, okay? So this would be our conjugate acid, this would be our conjugate base. Down here, ammonia will actually take the hydrogen and become ammonium. So the ammonium would be the conjugate acid, whereas the ammonia, the NH3, would be the conjugate base. Okay, so the conjugate base is going to be something that has the ability to accept a proton, which in this case is the ammonia, and in this case it's the acetate. The conjugate acid is going to be the one that has the ability to donate a proton, which in this case is acetic acid, and in this case is ammonium. So the question is, like at this point, well, all right, let's actually mix an acid and a base together. So we have hydrochloric acid and we have sodium hydroxide, acid, base, right? So how does Arrhenius define these reactants? Take a moment to think about that. How does Bronsted and Lowry define the reactants? Okay, take a minute to think about that. So write out the reactants and then write them as their ionic components. So take a moment to do that too. So you can actually see this at the bottom, but maybe do that on your own without really looking at the bottom. So Arrhenius defines hydrochloric acid as the acid because it releases hydrogen in solution. And he also defines sodium hydroxide as a base because it would release the OH minus in solution. Bronsted and Lowry define them as the same acid and base, but because HCl would donate a proton, making it the acid, and then NaOH would break apart and form the hydroxide, which would accept a proton, and that would make it the base. Okay, so the ionic components, we have H plus, Cl minus, Na plus, OH minus. So we have them all down there. And we are going to form H2O, right? OH plus H, H2O, and then the sodium and the chloride are just going to remain in solution. So they would be our spectator ions. So H plus OH minus yields H2O liquid. That would be our net ionic equation. Okay, but what happens when we actually add acetic acid to potassium hydroxide? So acetic acid is a weak acid, but potassium hydroxide, that is a strong base. So what will happen? Well, potassium hydroxide is such a strong base that it will actually pluck all of the hydrogens off of the acetic acid. It kind of forces it. So our potassium hydroxide will react completely with the acetic acid and take all of the protons that are available. So we would go from HC2H3O2, acetic acid, plus KOH, or potassium hydroxide, and we would form potassium acetate and water. So anytime you use a strong base or a strong acid, it doesn't matter if we're working with a weak base or a weak acid, it will react completely with that other species. Okay, so the next two, I have some example problems, and I do have the solution written down here, but feel free to try this out on your own, okay? Plus, my solution down here looks real ugly because I just wrote it out all in one line. But anyways, what volume of 0.500 molar calcium hydroxide solution is required to neutralize 30.0 milliliters of 0.120 molar hydrobromic acid solution? Let's write out the chemical equation. So we have HBr and CaOH2 that will yield calcium bromide, CaBr2, and H2O. Balance, we'd have 2 HBr and 2 H2O. So what we will need to do is we will need to take our known 30.0 milliliters, let's convert that into liters, and then multiply by the concentration to get the number of moles of hydrobromic acid. All right, 30 times 1 over 1,000 times 0.120. Then we will take the mole ratio, which is 1 mole of calcium hydroxide for every 2 moles of hydrobromic acid. That'll give us the number of moles of calcium hydroxide. And then we can just multiply that by the molarity, and that will give us how many liters of calcium hydroxide that we would need, which in this case ends up being 0.0036 liters or 3.6 milliliters. Same thing over here. In this case, we just have perchloric acid, and we have potassium hydroxide. So perchloric acid, HClO4, and potassium hydroxide, and that will give us potassium perchlorate and water. So take our known 10 milliliters, convert that into liters, then convert that into the number of moles of potassium hydroxide that we have. Use the mole ratio that we have here, and then multiply that by the molarity, and that will give us the number of liters that we would need of perchloric acid. Okay, so that's all written out here. And you would need 20.2 milliliters or 0.0202 liters of perchloric acid. All right, well, that is it for our acid and base reactions. We will talk a lot more in detail with this in Unit 8, but for right now, that is as much as we are going to get to. And you will have redox next.